Today we are covering the second part of the thermodynamics. In the last lecture, we've discussed about thermodynamics' first law that energy is conserved and it cannot be created or destroyed. Today we're going to talk about the thermodynamics' second law that spontaneous processes are characterized by conversion of order to disorder. Even though you see the opposite trend in some isolated part of the universe, that must be followed and compensated by the entropy or S increase elsewhere. And this entropy or S, indicative of disorderedness, is another critical state function for the thermodynamics. To explain better about this entropy, we need to talk about the disorder, which is indicated as W here and is measured by the number of energetically equivalent ways to arrange the system. And this W is really hard to measure. Let's look at an example here with the two bulbs connected to each other. And there's a stopcock here, so the gas molecules are only in one of the bulbs. But once this stopcock is open, now all the gas molecules can diffuse to the other bulb, which increases the disorder because now all of the molecules have many more ways to be present. And this results in the increase of the entropy too. And degree of randomness is expressed by this entropy or S. And here's the formula that you can use to basically get the entropy, where the Kb is the Boltzmann constant and W is the disorder. And again, this W can be hard to measure because there are a lot of numbers, all the almost infinite number of possibilities that molecules can exist. So using this formula, it's hard to get S2. Anyway, S depends on the temperature because increasing the temperature actually increases the W2. So entropy's unit is in K2. Again, the second law is about a conversion from order to disorder. And by this second law, if there's a spontaneous process with no changes in enthalpy or internal energy, then entropy changes should be positive. But a process can still occur spontaneously even if delta H is positive, meaning that its reaction is enthalpically opposed or endothermic. But it still happens only when the entropy change is positive and also large enough to outweigh the enthalpy change. An example is an ice pack here. Upon the reaction, it absorbs all the energies from the surrounding, so definitely the delta H is positive here or endothermic. But it still happens because the reaction itself, which is a dissolution of urea, creates a lot of positive changes in entropy, which outweighs the delta H. The same thing, same principle applies to the entropy in biology too, but we cannot measure W directly in the cell. Again, it's hard to count all those possible numbers and possibilities where the molecules exist. So instead of that, we have an expression only at the constant temperature conditions. So for the spontaneous process, here's the condition where delta S, the entropy change, is larger than Q divided by T, where the Q is heat and the T is a temperature. And if the pressure is constant, just like the most cells, then it should be changed to delta S is larger than Qp, the heat at a constant pressure, divided by T. So can we predict the spontaneity from the entropy change? The answer is no. Let's look at an example here where two hydrogen molecules and one oxygen molecule get together to become two water molecules. When you look at the total number of molecules, it changes from 3 to 2, so the disorder actually goes down instead of going up, but it still occurs spontaneously. Then how do we resolve this problem? To do so, we bring back this expression, delta S is larger than Qp divided by T, but we can change this Qp with delta H from this expression that we got in our last lecture. So the delta S is going to be larger than delta H divided by T at a constant pressure. And we can rearrange this T and all of them here to get the delta H minus T delta S is smaller than 0. And this is the true criterion for the spontaneity, which was figured out by J. Willard Gibbs. Gibbs introduced a new really important state function called Gibbs free energy, or free energy, often defined as energy available to the work. So the Gibbs energy can be written as G equals H minus Ts, and its changes, the Gibbs free energy is delta H minus T delta S. And for the spontaneous process, the delta G should be negative. And when you look at the Gibbs free energy here, the product of T and delta S, the entropy change, has to be larger than delta H, or the enthalpy change. Let's look at some classifications of reactions here. If delta H is positive, that means the system absorbs the energy, so it's an endothermic process. If delta H is negative, the system loses the energy, meaning that it's an exothermic process. If delta S is positive, that means the disorder increases. And lastly, if the delta S is negative, that means the disorder decreases. And the spontaneity, basically, which is the Gibbs free energy of the reaction, depends on the delta H and delta S values, as you can see here. This table shows the relationship between delta H and delta S to get the delta G Gibbs free energy. And I also put the delta G here too. So when delta H is negative and delta S is positive, when you put the values here, then delta G should be negative all the time. And that means that reaction is both enthalpically favored, endothermic, and entropically favored, meaning that delta S is positive and this reaction goes to more disordered state. And this reaction is spontaneous or endergonic at all temperatures. Let's look at the bottom one where delta H is positive and delta S is negative. In that case, delta G is going to be always positive, and that means this reaction is always non-spontaneous or endergonic at all temperatures. And for these two conditions, depending on the temperatures, it can be either spontaneous or non-spontaneous reactions. When the delta H and S is both negative, temperature has to be below delta H divided by delta S, which was gotten from here, to get the spontaneous reaction. If the delta H and delta S are both positive, then temperature has to be above delta H divided by delta S to get the spontaneous reactions. So I want you to spend some time here to plug these positive or negative values into this delta H and delta S to see that how delta G changes and the relationship with the T here, the temperature. So here's a summary. Spontaneous processes are exergonic, so the delta G is negative. And non-spontaneous processes are endergonic, so the delta G is positive. And for a reversible reaction, if one reaction is exergonic, the opposite reaction should be endergonic and vice versa. And if the reaction is at equilibrium, that means G equals 0. But the thermodynamics does not tell you anything about the rate of the reaction or the speed of the reaction. It only tells you the spontaneity or the direction of the reaction. And even if delta G is negative, that does not mean that the reaction will occur with the rapid speed. Here's an example that diamond can be converted to the graphite because this reaction is exergonic. But the rate is infinitely low, so you don't need to worry about your diamond and get decayed. And we also talked about these four state functions for thermodynamics. U, internal energy, H, enthalpy, S, entropy, and G, Gibbs free energy. And these all four state functions are independent of path the system took to get to that state. But only the changes of these state functions are measurable, not the absolute values. And for a given reaction, those four changes are also independent of the path the reaction took. Only the starting and final states matters. Here's an example that glucose is digested to the carbon dioxide and the water here, which generates this much of energy here. And there are a lot of different processes happened, but it really doesn't matter about that intermediate stages. It only cares about from the beginning to the end to get the free energy here. And also in biology, it is almost impossible to precisely measure the delta H on every step because, of course, there are a lot of steps exist in the body and the biological processes. And the energy is usually released gradually instead of releasing all of them at the same time. And there are other biochemical reactions also occur simultaneously in the body, so it's hard to distinguish the energy generated from this particular reaction to the other. But since it is a state function, this value can be obtained by burning glucose in a calorimeter bomb and can measure the amount of heat that is released. And the free energy of a formation is basically additive. So you can get the delta G of the reaction by getting the sum of all the delta G from the products and subtract that by the sum of the delta G from the reactants. And there's a table listing out many different kinds of substances with their delta G values. So you can calculate the delta G of the reaction from them by addition or the subtraction. An alternative way to get delta G is to get it from KEQ of the reaction, where KEQ is the equilibrium constant or dissociation constant at equilibrium. And it can be obtained by the concentration of all the products divided by the concentration of all the reactants. And Gibbs energy is related to the concentration of the reactants and products. Let's take a look at an example here where the two bulbs are connected to each other here. And a collection of gas molecules occupies only one of the bulb, but once the stopcock is open, now these all molecules diffuse to the other bulb, which lowers the concentration of gas molecules and consequently increases the entropy, and vice versa too in this reaction. And as you can see in this formula, the changes in entropy directly affects the delta G values. So the relationship between the KEQ of the delta G can be written as delta G equals delta G naught plus RT ln concentration of all the products divided by the concentration of all the reactants. And here the delta G naught is the delta G value at a standard state. And the standard state we're going to discuss about that later in this lecture. And the R is the gas constant, as you can see here, and the T is the temperature in Kelvin. So for a reaction with reactants A and B and products C and D, it can be written as AA plus BB changes to CC and DD and vice versa too, where these little A, B, C, D are basically coefficients and they are the stoichiometry for each molecules for the reactants and the products. Then delta G can be written as delta G naught plus RT ln concentration of all the products divided by the concentration of all the reactants. And here A, B, C, D, their concentrations are actual prevalent concentrations in the cell at the moment. They are not equilibrium concentrations. And delta G naught is the delta G at standard state, like I told you in a previous slide. Here we quickly define the standard state. That can be defined as the state where the pH is 7 and the temperature is 25 degrees C, which is same as the 298 Kelvin. And all the reagents should be present at 1 molar, including the media such as water too. But it's different than biochemist's standard state, which we're going to discuss more in depth in the later of this lecture. So let's say that all the reagents are at the standard state, so they should be at 1 molar. A, B, C, D all should be just 1 molar. Then delta G is going to be delta G naught plus RT ln 1. because all of them, these are the same as 1. And as you know, ln1 is 0, so basically it cancels out whole this region. Then it's going to be delta G equals delta G naught, meaning that the Gibbs free energy is going to be same as the Gibbs free energy at the standard state. But keep in mind that this delta G is the constant value because this is just a one Gibbs free energy value particularly at the equilibrium state. But the concentration of the reactants and the products can be changed. So RT, ln, these values are variable. Can a reaction proceed spontaneously even if its delta G naught is positive? And here's the formula to get the delta G. And answer is yes, but only when its delta G in the cell is negative. So this value is negative. But to get this delta G is negative, because delta G naught is positive, this RT ln CD over AB should be a negative value, and this value has to be bigger than delta G naught to get the overall delta G as a negative value. And to get this RT ln CD over AB as a negative value, this R, the gas constant, and the T temperature are both positive values, so ln value has to be negative. To do so, CD over AB should be smaller than 1. And to get that value, get that small value for this, either A and B, the reactants has to be a lot of them there available, or there are just a little bit of a product in terms of its concentration has to be present in the cell. And to get this reaction products, the C and D, much lower values to boost this delta G as a negative value. This C and D has to be cleared up. So to do so, in many systems and the pathways in the cell utilizes biochemical pathways to use this reaction product C and D as a reactant for other following reactions or the pathways. In that case, it'll clear up the CD, so it'll keep this level really small. At an equilibrium where delta G equals 0, the concentration of reactants and products are constant, although its reaction itself is pretty dynamic, and that means they are equilibrium concentrations. Thus, you can write it as CD over AB as just the equilibrium constant, or KEQ. And sometimes people use EQ suffix right next to all the concentration values here, but this subscript is often omitted. Now let's substitute this KEQ, which was this value, into the formula to get the delta G here. And the delta G is going to be 0, of course, at equilibrium. So it's going to be just 0 equals delta Q naught plus RT ln KEQ. And you can rearrange these values to get the delta G naught equals minus RT ln KEQ. And now let's transpose and rearrange again to get the ln KEQ value, which is right here, to move the minus RT over to the opposite side to get the minus delta G naught divided by RT. And to get the formula of only the KEQ, you can transpose this ln into here to get the KEQ equals E to the minus delta G naught divided by RT. Now you can see the relationship between the KEQ and the delta G naught. And if you know one of these values, you can simply calculate the other values by plugging those values in this formula. Now note that the relationship between KEQ and delta G naught is inverse and exponential, as you can see here, because it's the exponential function with the negative values in front of this delta G naught. So it can be rewritten as this 1 divided by E to the delta G naught divided by RT. And what are the consequences of this inverse and exponential relationship? So that means even a small changes in delta G naught right here can result in a huge changes in KEQ because it's an exponential function. And if delta G naught is large and positive, that means this value will be much smaller. So KEQ becomes really small. And that also means that the reaction goes to the left direction. So the reverse reaction is favored in this case at standard state, which is for the delta G naught. And if the delta G naught is large and negative, now think about that this value is large, but it's a negative value, so it's going to be ended up having a huge value for this. So KEQ becomes really large, and that can lead to the reaction goes to the right direction in this case, which is a forward reaction. And it also happens at the standard state because everything is happening with the delta G naught, which is the delta G at a standard state. Let's look at a table showing the relationship between KEQ and delta G naught. Like I told you, KEQ and delta G naught have an inverse and exponential relationship here. So as you can see, as KEQ becomes larger and larger, the delta G naught values actually get smaller and smaller to the negative values. And also, even a small changes in delta G naught results in a huge changes in KEQ. But in the actual cells, this is not about the equilibrium where the KEQ and delta G naught is involved many times. But the reaction itself depends on the more like actual reactants and products, which is not met the equilibrium state. So please go back to this formula again and remember it, that delta G equals to delta G naught plus RT ln CD concentration divided by AB concentration, the ratio of the products and the reactants. Now let's consider some other state function, delta H and delta S. Now we can basically determine this enthalpy change and entropy change of a process using this relationship between the delta G naught and KEQ. So from this expression, let's rearrange values here to get the ln KEQ, which is right here, and move this into here, equals minus delta G naught divided by RT. But remember that the delta G equals delta H minus T delta S, where you can get the Gibbs free energy. And at the standard state, delta G is going to become delta G naught, and everything is going to be at the standard state. And so delta G naught equals delta H naught minus T delta S naught. Now we have this delta G naught and plug this into here in this expression to get the ln KEQ equals minus H naught divided by RT. So now this one comes here and replacing this, and plus instead of minus because there was a negative value in front of it, this and this expression. So it's going to be plus delta S naught divided by R, because T is going to be canceled out from here and here. And this expression now looks more like a linear function of the type y equals kx plus b, where this y is going to be ln KEQ, and here the x value is going to be inverted t right here, and k is going to be right here, the minus delta H naught divided by R, and lastly the b is going to be delta S naught divided by R. Again, this is the expression to show the relationship between KEQ and delta H naught and also delta S naught. And from this linear plot of ln KEQ on y-axis as a function of 1 over t on x-axis, you can determine the slope here, which is a coefficient of x variable, as a minus delta H naught divided by R. And from here, you can get the delta H naught by putting in the unknown value for the KEQ. And sometimes this can be plotted as R ln KEQ instead of just ln KEQ. by moving the gas constant over to the other side of this equation. And the Bentov plot actually uses this relationship and the exact same linear plot. But to plot this Bentov plot, you need to determine the KEQ values at many different temperatures. So you can put the values right here and put it in this linear plot. And this way, you can get the delta H naught values much easily than the calorimeter, where you need to burn things and have to measure things for all different kinds of substances. But this calorimeter is, again, a much more direct way, so it'll be ended up like a combinatorial way to determine the delta H naught values for substances. So what is the standard state? Earlier this lecture, I've briefly mentioned about the definition of the standard state, but now let's talk about it in much more details, especially in the context of the biochemistry. In chemistry, the standard state is a state where the temperature is 25 degrees C and the pressure is 1 atmosphere and all the reagents are at 1 molar concentration. But biochemists found that these conditions are too extreme and not so relevant to the cellular systems and the living organisms. So they had to come up with a modified version of the standard state, and its notation is delta G naught prime, but it's often written as just a G naught prime in biochemistry. So now let's take a look at the differences between the chemist's and biochemist standard states. In biochemist standard state, activity is assumed to be the same as concentration. And I'm pretty sure you already know the term activity that you learned from the organic chemistry or the other chemistry classes. But activity is the effective concentration or the concentration that is corrected for its non-ideal behavior at concentrations higher than infinite dilution. Meaning that if there's a molecules in a space and there are multiple of them, then one molecule can affect the other molecules in terms of their behavior. Let's think about the Brownian motions, which can freely move here and there if there were to be just one molecule. But if there are many of them, especially in a high concentration, the Brownian motion will be limited because of the other molecules in the vicinity. So in that case, all these non-ideal behavior has to be corrected and applied to the concentration here to get the effective concentration, which is activity. But in the cells and other cellular organisms, many times concentration of reactants and products are quite low in millimolar or micromolar ranges. So biochemists assume that activity is the same as concentration. Secondly, the activity of a pure water is assigned a value of 1, even though the actual molar concentration is 55.5 molar for the pure water. And it makes everything simple and easy to calculate because now the term concentration for the water is always 1 and can be simply ignored in many cases. And this is particularly important because all the reactions in the cell happens in the water as a medium. So you're going to see always the concentration of water. If that were to be a different number, it wouldn't make the other calculations a little bit more complicated. And third, the hydrogen cation activity is set to 1 at pH 7 instead of at pH 0, because in chemistry, pH 0 really corresponds to the 1 molar of hydrogen cation, but no biochemical reactions occurs in such extreme environment. So we actually set it as 1 of the H ion activity at pH 7, the neutral pH, which most often cases in the cell. And lastly, for the ionizable substances, their biochemical standard states are defined in terms of the mixture of their ionic species at pH 7, not in terms of individual ionized forms, because it is hard to measure those individual ionized forms and their activities. Remember that delta G gives free energy, predicts only spontaneity, but it does not say anything about the rate or the speed of the reaction. Let's take a look at these two examples. First one's glucose that is digested to the carbon dioxide and water, and it produces a lot of energy, meaning that the delta G is highly negative, and it's an exergonic process, meaning that it's a spontaneous process. But the glucose on the left shelf can sit for years in contact with oxygen, and of course it shows no signs of decomposition, meaning that delta G, although the value is negative, it does not say anything about the rate itself of the reaction. Same thing applies to the diamond changed to graphite. It is an exergonic process. Delta G is negative. As you can see, it generates the energy after this reaction, but it rarely happens, almost in no cases. And there's a conversion from the diamond to the graphite without catalyst, because again, the delta G does not tell anything about the rate, and this process has a really low rate. But the catalyst actually speeds up the rate or the speed of the reaction to get to the approach to the equilibrium. But catalysts, in contrast, do not change the delta G of the reaction. So here's the biochemist view of thermodynamics. First, life obeys the laws of thermodynamics, regardless of the size of the molecules or the types of the molecules. And living organisms require energy, especially for the endergonic processes. And biochemists study the processes by which energy is extracted, channeled, and consumed by living organisms. So we look at the energy changes in chemistry in the living system. And lastly, the thermodynamics and bioenergetics give us a way to describe, characterize, and understand the energy changes in any biological reactions. So biochemical reactions happens everywhere, inside of the organisms and outside of the organisms too. And living organisms are basically open system maintaining a steady state, so-called homeostasis. So even though it looks like it met the equilibrium, there are a lot of flows of substances and energies that constantly going in and out. And the energy generated from the sun that gets to the plants for the photosynthesis, and that energy is consumed by the animals by the breakdown of the carbohydrates. And after that, these animals loses these energies by the heat loss. And there's a cycle for that forever in the universe. And here's the summary of what we've learned so far. For initial energy, the change of the initial energy is the U final minus U initial, or the Q minus W. Q for the heat that the system gained, minus W, the work the system has done. And enthalpy changes is going to be written as delta H equals delta U plus P delta V. And also this enthalpy changes can be written as QP at a constant pressure, meaning that enthalpy change is the same as heat transferred at constant pressure. And for the entropy, S is KB, Boltzmann constant, ln W, and this is a measure of randomness. And free energy, the Gibbs free energy delta G equals delta H minus T delta S. And it's a criterion for spontaneity. And predicting spontaneity is different from predicting rate or kinetics of the reaction. And delta G tells you nothing about the rate of the process, but it only tells you about the spontaneity. And the fact that the delta G is negative does not mean that the reaction will go faster. Again, it's not about the rate. And if the process is at equilibrium, its delta G equals 0. Delta G is related to the delta G naught, so the Gibbs free energy is related to the Gibbs free energy at the standard state using this expression. And this expression can be changed to the more general form here as delta G equals delta G naught plus RT ln concentration of all the products divided by the concentration of all the reactants. And the delta G naught is related to the KEQ here using this formula. And this formula was used for the Van plot where you can determine the delta H naught value. And lastly, the free energy of formation is basically additive. So to get the delta G value of all the reactions, what you can do is to get the delta G value of all the products and get the delta G value of all the reactants and subtract one from the other to get the final delta G value.